So let's think back to 1986 for a second. The Challenger launch.
Oh yeah, tragic.
73 seconds in. And it all came down to what? A rubber O-ring?
A tiny component failed because of the coal.
Exactly. One small failure, but catastrophic consequences. 7 lives lost, the whole shuttle.
It really became the textbook example, didn't it, across so many fields of a single point of failure, a SPOF.
It did. And that concept, SPOF, it's just as critical, maybe even more so in cybersecurity today.
Absolutely vital. Because, these digital infrastructures we rely on, they're complex. And these single points of failure, they can just be lurking, unseen.
Until they fail, or worse, get compromised.
Right. And then the fallout can be huge, toll disruption maybe, or even subtle long-term breaches that nobody spots for ages.
Which is exactly what we want to dig into today, this whole idea of single points of failure in modern cybersecurity. We're going to explore this really interesting graph-based way of finding them and talk about why getting a handle on SPOS is just fundamental for any solid security strategy.
And this isn't just theoretical, right? We're basing this on a specific analysis, even looking at a real-world case from 2025.
We are. So let's make it concrete. When we talk about SPOFs in cyber, what kinds of things are we actually, referring to?
Good question. Think about those core systems everything else depends on.
Like authentication servers.
Exactly. Like Active Directory, managing who gets access to what in a company. Or in mobile networks, the HSS, the home subscriber server, holds all that key subscriber info.
So if AD goes down or gets hit, chaos.
Total paralysis for the organization, potentially.
Yeah.
Or if an HSS is breached, you're looking at massive data exposure.
Okay, what else?
Well, think about update tools, SCCM, for example, if an attacker gets control of that.
Oof. They could push malware out to basically everything.
Precisely. It's like handing them a master key for software deployment.
And it's not just servers and software, is it? It's the network plumbing, too.
For sure. Gateway routers, for instance. The main doors in and out of your network.
If that goes down,
you're cut off. Or if it's manipulated, traffic gets rerouted, intercepted. Big problems.
And cloud architecture. I hear people talk about single region setups.
Yeah, that's another classic SPOF. If you put all your eggs in one cloud region basket, and that region has a major outage,
your entire cloud presence just vanishes.
It could. So the common thread is this central dependency. Too much relies on one single component. That's your SPOF.
Okay, got it. So we know what they look like. But finding them in these huge, complex systems, that sounds tough. How does this graph approach actually work?
Right, so the core idea is pretty neat. You model your whole cybersecurity setup as a graph.
Like a map.
Kind of, yeah. Each asset, PC, server, firewall, whatever is a node, a point on the map.
And the connections between them.
Those are the edges, the lines showing how they communicate, what depends on what.
Okay.
And the analysis we're looking at use specific tools and this graph.json file, which, by the way, you can find on GitHub in the SPOF and Cybersecurity repo if you want to explore it.
Oh, cool. So they use this file to, simulate things?
Yeah, exactly. To simulate what happens if different parts of this map, different nodes, get taken out or compromised.
And did they model, how an attacker might move through this graph?
They did. They used a pretty standard attack flow.
Like getting in, moving around, stealing data.
Pretty much.
Yeah.
Entry first, maybe exploiting something. Then getting inside access, VPN or VDI maybe.
Then grabbing more privileges.
Yep, privilege escalation. Then maybe planting malware. And finally, the goal for many attackers, getting data out, data exfiltration.
So by mapping all the possible ways an attacker could follow that chain,
you start to see which nodes keep popping up, which ones are essential steps on lots of different paths. Those are your potential choke points.
Now, the really intriguing part for me was how they built these graphs. You mentioned LLMs like ChatGPT.
That's one of the coolest parts, I think. Building these maps used to be so much manual work. Really tedious.
Right. Someone had to draw it all out, basically.
Or piece it together from spreadsheets and docs. But here, they fed the LLMs existing documents.
Like network diagrams, audit reports.
Exactly. Firewall rules, security reports, network descriptions written in plain English. And the LLM could automatically pull out the assets, the nodes, and how they're connected to the edges.
Wow. So it automates the map making.
A huge chunk of it, yeah. Apparently, even simple prompts worked surprisingly well.
Like what kind of prompt?
Something straightforward like, extract assets and their logical connections from the following network description.
And it would just spit out the nodes and edges.
In a structured format like JSON, ready for the analysis tools.
Mm.
Now, obviously, they stress that humans still needed to check it. You need that manual review for accuracy.
Of course. But still, that speeds things up massively.
Hugely.
Okay, so graph built, attack paths mapped. How do we get from that to actually identifying the SPOFs? What's the method?
Right, this is where it gets analytical. It's called weighted path enumeration and node removal simulation. Bit of a mouthful.
Let's break it down. Path enumeration.
First, find all the simple paths an attacker could take from an entry point to an exit point, like data exfiltration. Just list them all out.
Okay, then?
Then, for every node inside those paths, not the start or end point, but the steps in between, you count how many different paths it appears on.
Ah, okay. So if a server sits on 100 different attack routes, it's probably important.
Exactly. But there's another layer, weighted paths.
Meaning, not all nodes are equal.
Precisely. Compromising, say, a regular Office PC versus a critical domain controller. Very different impacts, right?
Definitely.
So they assigned weights. In their case, an Office PC, OAPC, got a tiny weight, like 0.0005. But a server got a weight of 1.0, much higher.
So the paths involving critical servers count for more in the analysis.
You got it. It prioritizes the operational significance of the assets.
Okay, weighted path counting. What about the node removal simulation?
This is the key part for spotting SPFs. They computationally remove each node from the graph one by one. Just pretend it's gone. And after removing a node, they recalculate how many attack paths from entry to exfiltration are still possible in this broken graph.
Ah, so you see how much damage removing that one node does to the attacker's options.
Exactly. The percentage drop in reachable paths when you remove a node tells you how critical it is as a SPOF. If removing it wipes out, say, 60% of the paths, that's a major SPOF.
So it's not just if it's used, but how much the whole attack surface shrinks if it's gone.
Precisely. They mentioned it's like a practical, cybersecurity-focused version of Betweenness centrality from graph theory. But instead of abstract math, it's tied directly to attack scenarios, like finding the key bridge in a city, remove it, and how many routes get blocked or massively rerouted.
And this leads to that color-coded visualization you mentioned, red, yellow, blue.
Yep. Red nodes were absolute SPOFs. Removing them cut off more than 50% of the paths. Huge impact.
Yeah.
Relative SPOFs. Still significant, but maybe less devastating than red.
Blue.
Redundant, but impactful. Meaning important, but maybe there are other ways around if it fails. Still needs attention, though.
And gray is low priority.
Right. It gives you this instant visual guide to where the biggest structural risks lie, like an X-ray of your network's weak points.
Did the analysis actually call out specific nodes that were big hubs?
Oh, yeah. Based on, I think, 470 path samples, some nodes just kept showing up as critical crossroads.
Such as?
An intranet MGMP server was in almost 62% of all paths.
Wow. Likely managing internal systems.
Probably. Then a server access gateway controlling access to servers was in over 55%.
Makes sense.
And, maybe more surprisingly, Nutanix, a hyper-converged infrastructure platform, showed up in just over half the paths.
Huh. Nutanix, you might not immediately think of that as a primary target.
Right, and that's a key insight. These critical structural nodes, these hubs, might not be the ones generating tons of noisy alerts day to day, but for an attacker moving through the network, they're essential.
So, stepping back, what are the big picture insights from doing this kind of graph analysis?
Well, several things. First, different graph metrics give different kinds of intel. Between Narnana centrality, like we said, nails the SPOFs.
Right, the choke points.
But something like closeness centrality can show you nodes that could spread malware really fast, or nodes that are good spots for deploying defensive actions quickly.
Okay. What about degree centrality? Just how many connections a node has?
That tells you about common access points, maybe, but doesn't automatically mean it's structurally critical for attack paths. High traffic doesn't always equal high impact if it fails.
Interesting. And PageRank, like Google uses.
Yeah, that can highlight nodes that are highly trusted by other important nodes. Think authentication systems, certificate authorities. Compromising those can have cascading effects.
But the killer insight seemed to be this idea that visibility impact.
Absolutely fundamental. So much security effort, so many alerts, so much budget often gets thrown at endpoint devices, those Office PCs, right? Because they're noisy, they get infected easily, users click things.
They generate alerts.
Exactly. But this analysis shows those endpoints, while needing protection, might have limited strategic value compared to a central server or gateway that enables movement across the entire network.
It's like focusing on the petty thieves while the main vault has a weak door.
Perfect analogy.
Ugh.
And that leads directly to the problem of hidden SPOFs.
Like the Nutanix example.
Right. It's in half the attack paths, potentially a crucial stepping stone, but maybe it's not lighting up the security dashboards every day, so it gets overlooked.
Because everyone's busy chasing the alerts from the endpoints.
Uh-huh. And that naturally leads to misaligned budgets.
Spending money on the noisy stuff, not necessarily the most critical structural stuff.
Precisely. Pouring resources into endpoint detection, which is important, but maybe underinvesting in the resilience of that core infrastructure, those central servers, gateways, management tools, the real SPOFs.
It's about shifting from just reacting to edge noise to proactively shoring up the core.
Exactly.
You mentioned a real-world example, the SK Telecom breach in 2025. How does that tie in?
Yeah, that was reportedly a major incident. Attackers apparently got access to a huge amount of SIM authentication data for SK Telecom customers.
Oh, sensitive stuff.
Very. And the analysis we're drawing from suggests that investigations pointed towards a centralized HSS, that home subscriber server we mentioned earlier, acting as a key SPOF.
So one central point holds all that critical data.
And the indication was maybe there wasn't enough focus or investment on making that specific component redundant and resilient. Its compromise had massive consequences.
Which illustrates that reactive pattern, right? Big breach happens, then everyone scrambles to fix the hole.
Exactly. Instead of doing the architectural assessment beforehand to find and fix those SPOFs proactively before they become headlines.
This really highlights why having clear SPOF categories and response plans is so important. How did the analysis define those categories?
They had pretty clear criteria. Absolute SPOFs were the top tier. A node was absolute if removing it killed at least 80% of attack paths.
80%.
Yeah, huge. Or if it was involved in paths covering over 30% of the total weighted path coverage. Remember the weighting for critical assets.
Right, so it considers both frequency and the importance of the assets involved.
Correct. It's not just about path count, but potential impact.
And then they had 4 tiers based on that, with different strategies.
Yeah, tier 1, absolute. Like that intranet MGMT server causing a 50% path drop. Strategy, redundancy, serious hardening, make it rock solid or have backups.
Tier 2.
Relative SPOFs, think SCCM, AD, Nutanix, path drops maybe 20, 50%. Strategy here is more about microsegmentation contain the blast radius, if it is compromised, and tighter access controls. Limit who can touch it.
Tier 3.
Redundant, but impactful. Things like maybe shared workstations, VPN concentrators, drop rate 10, 20%. Here, the focus is more on enhanced monitoring. Keep a close eye on them.
And the last tier, low.
Yeah, things like standard VDI terminals, less than 10% path drop. Basic security controls are likely sufficient here. Don't overspend.
So it's a really practical, risk-based way to prioritize effort and budget?
Totally. It guides you where to put your resources for the biggest structural security improvement. No more guessing or just reacting to noise.
So, wrapping things up, the main message here feels like identifying SPOFs isn't just, a tech checkbox. It's core strategy.
It absolutely has to be. Real security isn't just about buying the latest tools to catch the latest malware. It's about building resilience into the design of your infrastructure.
Finding and fixing those structural weaknesses before they get exploited.
Before they become incidents.
Yeah.
And this graph method, it's powerful because it doesn't just find the problems, it helps justify the fix. You can actually estimate if we invest in making the server redundant, we cut our attack surface by X%.
That's valuable for making the business case.
Incredibly valuable.
So the big takeaway then, look beyond the alerts, understand the structure, address the SPOFs proactively.
Couldn't say it better. Which brings us to the final thought for you, the listener.
Yeah.
Given that these hidden SPOFs might be lurking even in networks that seem well protected, what steps can you actually take? How can you get a better, more holistic view of your own critical dependencies, your own potential single points of failure?
And maybe ask, are your security dollars really going towards the biggest structural risks? Or just the loudest alarms?
It's a crucial question to ask.
Definitely food for thought. And if you do want to dive deeper into the methodology itself, remember the code and tools are up on GitHub. Search for the SPOF in Cybersecurity repository.
Yeah, and there's plenty more to read up on too. Attack graphs, network centrality concepts, using LLMs for this kind of automation, general SPOF principles and architecture.
And those real-world cases like the Challenger Report or the CSIS Cyber Incidents List really drive home why this stuff matters.